what I want to do today is sort of recap what we've done so far with exponential functions, and then get into the next section, which is 4.3, which is entitled Logarithmic Functions. Uh, and all I want to do with logarithmic functions today is just get a good understanding of what they are, what they do for us, and some common calculations. So before that, exponential functions. So what did we do with exponential functions? We looked at what do they look like algebraically, right? So what do they look like algebraically? They look like f of x, some generic function name, equals a to the x. So the point is that the independent variable is in the exponent position. The part that's varying is up in the exponent position. That's what makes this different from a polynomial function. Okay, and we did say something about the base a. The base a has to be how did we say it? Where sorry, a is greater than 0. We don't want it to be negative, and a is not equal to 1. We don't want it to be 1 either. We don't want it to be negative because that would just be an awful way to define the function, right? That would get super, super complicated. And we don't want it to be 1 because if a is 1, then we don't have an exponential function. We would just have a constant function. So this is what they look like algebraically. The point is that the independent variable is up in the exponent position. We looked at how to evaluate them, so I'm not going to rehash all that, but we looked at how to evaluate these, basically like looking at plugging in numbers and how to evaluate them in the calculator. We looked at the graphs. So this is what the function looks like algebraically. We looked at graphs of exponential functions, and they typically fall into two categories. Well, they all fall into two categories. You've got the category where a, the base, is between 0 and 1. So some fraction like 1/3, 1/2, 1/5, 2/3, some fraction less than 1. And those graphs where we say, I may not have used this terminology before, but I'll use it now. They are exponentially decreasing. So they start super high, approaching infinity on this in the second quadrant. And they come down and they, go through that 0, 1 spot, and then they tend down to 0 as x gets larger. So we might describe this as exponentially. You might hear this decreasing. You might even hear this phrase out of math class, right? Something that's exponentially decreasing. Okay, and then we saw that when a is bigger than 1, here, when the base is bigger than 1, like 2 to the x or e to the x, that special number e that we looked at, or 3 to the x, or just any number bigger than 1 for the base, it's exponentially increasing. We could describe this as exponentially increasing. What else did we look at so far with exponential functions? We didn't really look at transformations too much, and that's okay. I don't think we need to dive into that too much, to be honest. All right, we looked next at applications. So we looked at some applications, and specifically the classic application to look at is compound interest. So we considered compound interest. a of t, some function of time. So time, if we're talking about an application for an exponential function, time better be in the exponent position, and it was. We had this equation, r over n times t, and we talked about that a fair bit and did some calculations, and we also talked about what happens when you let the number of compoundings, that n value, what happens when you let the number of compoundings get very large. And we see through some algebra that I probably swept under the rug, that when we have continuously compounded interest, which means n is approaching infinity, like n is approaching, instead of just having compoundings every day, it's every hour, it's every minute, it's every second, every millisecond, every nanosecond, continuously compounding, we had a new formula that involved that special number e. Oops. We had a of t equals p for the principal, the initial amount, times e, where e is that specific special irrational number raised to the RT. Okay. So again, I'm not going to like rehash that discussion because we've already talked about that, but so this is about as far as we went with exponential functions. We looked at some examples, we graphed some, and then applications, specifically applications as applications to savings accounts, right? Amount of interest earned in a savings account, which is what these formulas would be used for. Okay, and what else can I say that we did? Oh, actually, well, the connection from compound interest to continuously compound interest got us very nicely into that special exponential function with that base e. Sort of the e popping up here in continuously compound interest made us realize, oh, maybe this number e is important when it comes to exponential functions, and it very much is, and in fact so much so that if someone says the exponential function, they're talking about this exponential function, specifically the exponential function with a base of e, where recall that e is approximately 2.718. If you want more digits, you can go ask the calculator. You can say e raised to the first power, which would just be e, and it's 2.718281828, etc., etc. It's irrational. It never starts to repeat. It looks like it kind of starts to repeat here, but it doesn't because it's irrational. Okay, and we also saw, what else did we see? That the exponential function pops up all the time in outside of just continuously compound interest problems. It pops up when you're trying to model like the growth of a virus. I think we worked one of those problems. It pops up when you're trying to model radiocarbon dating. When you're trying to figure out how old something is, the exponential function pops up. It pops up when you're talking about populations of like animals or something. Just everywhere. It's just everywhere in science and math. If you get into any kind of STEM field, you will see the exponential function popping up in your field. Anything from business to chemistry, just everything. Okay, so now let's get into logarithms. So last time I said we want to look at problems where maybe we want to solve for the, let me say it like this. Let me write down the name of the section, and then I'm going to pose a question that's going to motivate the section. So 4.3 is called logarithmic functions. I found a really nice problem that's going to motivate this for us. It's motivation. Let's say, what is the time required to double an investment? So let's say you've got some investment or some money you're trying to drop into a savings account. Double an investment. At an interest rate of, I'm just going to make something that says 6% compounded continuously. So say you've got some savings account, it compounds continuously. The interest rate is 6%. And you want to know, how much time do I need to wait until my investment doubles? Okay. Let me read this again. What is the time required to double an investment at an interest rate of 6%? Yeah. Okay, so if we approach this with the tools that we have already, we know that if we're talking about continuously compounded interest, I know that I have this formula. A of t is equal to P times ERT. Okay, cool. So that's the formula. So let me say, I want, so here's something to know. A of t to be double of the initial amount, right? That's the question. The initial amount being P, right? The initial amount is the principal. We call it capital P. And the question is time required to double the investment. So what do I want A of t to turn into? Double the initial amount. So I want it to be 2P, right? I want to say we want A of t equal to 2P, right? Double the initial investment. So I'm going to replace that here. So far, this is going good. It seems like we're going to be able to get somewhere with this. I'll plug in 2. Okay, so I'm going to go ahead and say this looks good. I feel, pretty clever. Like replace this A of t with 2P because I know I need to double the investment. That feels pretty sneaky and like a really good thing to do. And moreover, I see that the P's can actually divide out on both sides here. I end up with this. And now I'll go ahead and plug in my rate, which is 6%. So I'll remember to turn that to a decimal, wrap it in parentheses and say times t here. And I'm feeling pretty good because I'm getting far. But what do I do at this point? How do I solve for t? You hit a roadblock, right? Because how do you solve for t when it's buried up in the exponent position? We have no tools for this yet. Other than just maybe like plugging in numbers and trying, a whole bunch of numbers, maybe graphing it or something. We have no like algebraic tools. I'm going to say, let's say that we have no algebraic tools to solve this, to solve for time, which is of course what the question asked for. Time. We have no algebraic tools to solve for t. When I say algebraic tools, I mean like an algebraic tool would be like dividing by 2, something like that you could describe and write down on paper. We have no tools to do this. This is the motivation for the section 4.3. Logarithms are going to be that new tool that we introduce in order to solve for things that are buried up in an exponent position. So I'll save this page and we will go back to it when we can. Probably come on Wednesday.
So here we go. Let's introduce logarithmic functions. Say what they do for us. Logarithmic functions I'll define it first. Let's say for base A, I'm going to write down the fancy definition and then I'll talk about it. Denoted by log with a little a subscript there. Is defined by log sub a of x equals y if and only if a to the y is to x. All right, that says a lot there, so let's think about this. And by the way, I need to say where the same thing that we said for a before, where a is greater than 0 and a is not equal to 1. That needs to be stated here too. Okay, so what is this saying? What is this saying? So logs allow us to solve equations like, say, 2 raised to the y is equal to, I don't know, let's make up some number that would be hard to figure out here, like 10. 2 raised to the y is equal to 10. Because 2 raised to the y is equal to 10 is the same as saying log of base 2 of 10 is equal to that value y. You know, I followed along the definition here. So what they do, why is this such a big deal? Logs undo exponential functions. Exponential functions stuff the input variable, the independent variable, up in the exponent position. When you take a log on both sides, which I'm gonna give you more details about like what that actually looks like algebraically, but what the log does is it gets the variable out of the exponent position and plops it by itself right there on the other side of the equal sign. It explicitly solves for the y value. Or in this case, it's the letter y because that's the up here to find the input of the exponential function, which is a little bit backwards, but that's how the book does it. So logs undo exponential functions. That's another way to say it here. Logarithms undo exponential functions. In particular, they are the inverse functions. They are inverses. They are the inverse functions of exponential functions. So pretty much what I want to do in this lecture is just practice using the definition of a log to get comfortable with what it's doing, because I could say this all day, but really what needs to happen is you need to practice it and see it being actually used before this idea really starts to settle in. So let's do some practice. Let's say example 1. Just rewriting exponential functions, or an equation in exponential form as a logarithm. Say 7 raised to the x is equal to 9. 7 raised to t raised to the t is equal to 10 raised to the x is equal to 10,000. 10 raised to the x is equal to 2 raised to the x, 64. So what the logarithm does for us is it's going to allow us to write each of these. It's going to allow us to write each of these with the input variable, which is up in the exponent position, explicitly solved for. That's the point. Every single one of these solutions I'm about to write down are going to say x equals something. And the something on the other side, while it looks kind of crazy because it's like a log with a base and like how do we compute that? We're going to get to that point. But for now, the point is just noting how all of these solutions are going to have that x, or t in this case, as I wrote it up here, explicitly solved for. So in the first case, 7 raised to the x equals 49 can be written as log base 7. The base always stays the same. The base of the exponential function, which is 7, will be the base of the logarithm of 49. So maybe I should write just to make it clear, the input of the log function is not the 7. That's the base of the log function. Base of the log function is 7. Its input is 49. This is equal to x. See how that exponent, the exponent position gets explicitly written right there. So it's explicitly solved for. We will later look at how to solve this. Right? We will look at how to solve this, equations like this later, but for now, we're just practicing rewriting these things. So similarly, this one will be log base 7 of 82 is equal to x. That's b there. All right, so let's consider A and B actually for a second in a little bit more detail. Notice that back here, you could probably figure out part A without ever knowing what the heck a logarithm is, right? Like if I asked you guys what x is, you could probably tell me after you thought about it for a second, right? X needs to be 2 in part A. X must be 2 because 7 squared is equal to 49, right? So maybe the logarithm does not seem so useful here. But think about, what is 7 raised to what power is equal to 82? Well, that's definitely not a whole number, right? It's somewhere between 2 and 3, because 7 cubed is much bigger than 82. So, but we have no idea what it might be, right? Somewhere between 2 and 3. This is why for equations like this that are not easily solved just by like looking at them and understanding how exponents work, this is where the logarithm is truly going to be useful and usually. Okay. Part C, we'll say log base e of 4 is equal to t. Later, we'll see that this log base e actually has a special name. Give it a name, but let's leave it be for now. Part D will be log base 10 of 10,000 equals x. So you see all of these, the exponent or that variable that was in the exponent position by itself explicitly solved for on the right side of the equation. Another log base 10, which you'll find the log base 10, we'll look later and see that log base 10 has a special name too. Log base 10 of 32 is equal to x. So again, looking at the difference from D to E here, part D you could solve for without using a logarithm. You could think about what do I need to raise 10 to be 10,000? No, it should be 10 times 10 times 10 times 10, which is 10 to the 4th. So x is 4. You could figure that out without ever knowing about logarithms, but you could not figure this one out without the use of logarithms. Right, and f here is going to be log base 2 of 64 is equal to x. We look at part A again and just interpret A in a different way. So part A said that 7x is equal to 7 to the x equals 49, and that can be rewritten as log base 7 of 49 is equal to x. Okay, that's what we had for part A and the solution for part A. So the log in this case can be interpreted as seven raised to what power equals 49? That's the question that the log is asking. When you write it in this form, just remember that that is the question that the log is asking. When you plug this into the calculator, which we don't know how to do yet, you know you have a log button on your calculator, but we need to, there's more discussions to be had about how to deal with a base of like 7 in this case. But once we figure out how to do that in the calculator, what the calculator is going to figure out for you is 7 raised to what power equals 49? Right, in this case, of course, we know it to be 2. But like I said earlier, once you branch out beyond those perfect whole number exponents, the question gets very hard to answer. And that's why it's these logarithms. All right. Let's do some more practice with actually evaluating logarithms that have nice relationships just to get a better feel for them. So, example 2. So this time I'm going to leave the leave it as an expression, and I'm asking us to evaluate each expression. So this is log base 10 of 1,000. Part B is going to be log base 2 of 32. Part C, let's say log base 10 of 0.1. That's interesting. That seems like it might be difficult, but we'll talk about it. And log base 16 of 4. That seems weird too. I'm going to introduce some more. Log base 2 of 1/8. and log base. Let's see, let's just end with a different one after all this difficult. Okay. So if I ask you to evaluate these log base 10 of 1000, you should ask the question, 10 raised to what power equals 1000? That's the question you're trying to answer. That's the question this log asks. So 10 cubed is equal to 1000, right? So log base 10 of 1000 is equal to 3. Because what 10 raised to what power is equal to 1000? Well, 10 raised to the third power is equal to 1000. So these are logs that can be computed without the use of a computer to help us. Computer being the calculator. All right, part B says log base 2 of 32. So that question is 2, the base, raised to what power? It's 32. So you think in your head, how many times do I have to multiply 2 by itself to get 32? Well, 2 times itself is just 2. So that's 2 to the first power is 2. 2 squared is 4, 8, 16, and then double one more time to get 32. So 2 to the 5th is equal to 32. So log of base 2 with an input of 32 gives an output of 5. Part C says, part C says log base 10 of 0.1. Log base 10 of 0.1 is asking the question, okay, so the base is 10, so 10 raised to what power equals 0. That is interesting, right? And you may think, oh, well, this must be one of the ones that we need a calculator to solve for. But we don't, because we know that 0.1 is equal to 1/10. Okay, so that means I'm going to go ahead and scoot this down. This is the one I'm solving here. 0.1 is equal to 1/10, but that is equal to, if I recall my exponent rules, well versed in those exponent rules, then I know that that is the same as 10 raised to the negative 1 power. The negative first power. And that exactly answers this question. 10 raised to what power equals 0.1? Well, I just answered it, right? It's negative 1. So log base 10 of 0.1, or 1/10, is equal to negative 1. Now, we're not going to look at graphs in this today. We're going to look at graphs tomorrow. Not tomorrow, Wednesday. Well, let's go ahead and note something. Logs and output negatives. We see it right there. They can output negatives. Let's keep going. It's just a note that we'll make use of. We'll make a bigger point out of this next time when we look at graphs. But for now, let's keep going with these evaluations. Log base 16 of 4. So I'm asking that base 16 raised to what power 4. So that's, again, interesting because it's smaller than the base, right? So how can this happen? 16 raised to what power is equal to 4? So I'm thinking of like 16 raised to something equals 4. Well, I know that square root of 16 is equal to 4, and square root of 16 is the same as 16 raised to the 1/2. I, again, need to recall exponent rules about radicals, right? So 16 raised to the 1/2 is equal to 4. These are just properties that you have to remember about exponents in order to be able to solve these problems. So since 16 raised to the 1/2 is equal to 4, then that means log, I've already answered the question, right? 16 raised to what power is equal to 4? Well, log base 16 of 4 is asking that question, and the answer is that exponent of half. Part E is saying log base 2 raised to the, or log base 2 of 1/8. So I want to know 2 raised to power is 1/8. So again, a chance to practice exponent rules. You need 1/8 written as some power of 2. So notice that 1/8 is equal to 1/2 raised to the third power. Right, 2 cubed is 8. Just keeping them both 1/, right? 1/8 is 1/2 cubed. And then now I need to get this as 2 raised to some power, right? Not just 1/2, but 2 raised to some power. But that's easy because I remember that I can just flip them and put a negative. Flip this and put a negative on the exponent. And now I have it. 2 raised to what power is 1/8? Well, 2 raised to the -3 is 1/8. So log base 2 of 1/8 is equal to -3. Okay. Finally, part F, which is going to seem very easy relative to these other ones. 5 raised to what power? It's 25. Well, we know 5 squared is equal to 25. Right, so log base 5 of 25 is equal to, because 5 squared equals 25. So hopefully you're getting a feeling now with those 6 examples of what the log is giving you, what it asks, and the answer that it gives. Okay. Let's look at some special properties of logarithms. Properties that are analogous to special properties for exponents. So let's think about some properties of exponents. Let's recall some properties of exponents. Anything raised to the 0th power is equal to 1, right? That's like one of those special rules. You raise anything to the 0th power, you get 1. Is there an analogous property for logarithms? Yes. Following that definition I gave at the top, we can say that this is the, rewrite this in terms of a logarithm. So log of base A, log base A of 1 is equal to 0. That's for any A. For any appropriate A, right? Like a positive A that's not 1, right? So the same restrictions on A that we had for exponential functions. What about A raised to the 1st power? Well, that's just itself, right? For exponents, that's the rule for exponent. You raise something to the 1st power, it doesn't change the number. over here, there's an analogous rule. It says log of base A, this A, of A is equal to what? Well, it's it's going to be 1 based off of what this says, but think about what the question is asking too. A raised to what power gives A? Of course, it's got to be. Okay, here are a couple more properties of logarithms that don't really have an analogous property of exponents over here. So here, well, here it is. Log of base A of A to the x. What is that equal to? We will use this a lot, this idea. Well, remember, the question is asking, it's saying this base, A raised to what power is A to the x? It's just x, right? Just x. Because it's like answering its own question. A raised to what power gives you A raised to the x? Well, the answer, you said the answer, right? It's the x, whatever the x is. So for instance, a quick example of that rule would be like log of 2 raised to 2 to the 17 would just be 2 raised to what power equals 2 to the 17th? Well, since the base and this input match, we can just, that exponent just pops right out. So it's this rule at work. Okay, and then we also have similarly a weird rule, if we won't use this as much, but it's still true. A raised to log base A of x is equal to x. It's just kind of like inverting this idea. So let's see how to interpret this. Up here in the exponent, it's saying log of base A of x. So A raised to what power gives you x? But out here we have that A raised to this entire thing gives us x, right? So it's just another, just showing how these things are inverses of one another. It's like canceling out here. If the base of the exponential function and the log function are matching, then they sort of cancel out, and you just get that input up there of x. Just it's the same as what's happening here, just in the reverse order. The log here is on the outside, and the exponential function's on the inside. Down here in this one, the log is on the inside, and the exponential is on the outside. So if I was to write an example of that rule at work, we could say 2 raised to log base 2 17 is equal to 17. Just using this rule. So I want to do some examples using these properties. So I'm going to try to this will be the last example today. Okay, let's evaluate each of these using these properties. For part A, log any base of 1 is equal to 0. So log base 5 of 1. For B, if the base and the input of the log are matching, then we just get 1. Because again, it's asking 5 raised to what power is equal to 5. C, sort of a similar rule, except the output's not 1 now, because the base and the input are still matching, except that the input is raised to an exponent. So we have that third property happening here. 8. Okay, and then part D, example, this last property, 5 raised to log of the same base. So base of the exponential is 5, base of the log is 5. We have some input of 12. And the answer to this, they're going to cancel each other out and just pop that input from that log. Okay, let me see what else I want to say. We got to talk about graphs and then the natural log, later the common log. Okay, cool. Making good progress. So that is it for 4.3 part 1. Next time we'll talk about graphs of logs, and we'll also talk about 2 special type of logs, and possibly get into a couple applications. And then Friday we'll start with the laws of logarithms, which is section 4.4. Any questions? If not, you are free to go.